Good evening. My name is Nona Martin, and I am Manager of Public Programs. And on behalf of the American Art Museum, I'd like to welcome you to this evening's program, a conversation with Internet Inventors. Before we begin, I'd like to share a few housekeeping notes with you. So I'd like to ask you to turn off your cell phones or any mobile devices. And I'd also like to share that we will have a question and answer period that will follow the conversation between Drs. Crocker and Cerf. Additionally, this program is being webcast live, and we'd like for our viewers and our audience to hear all the questions that are posed to our speakers. So we have arranged for our interns to provide microphones so that you can hear all the questions, and also our viewing audience can hear them also. As you exit the auditorium, you may be asked to complete a survey on the museum's public program. I'd like to thank you in advance for your cooperation. Finally, this program is in support of the exhibition, The Great American Hall of Wonders, and is in collaboration with the U.S. Patent and Trademark Office. We'd like to thank Postel for their important leadership support that they've provided for this exhibition and its public programs. The exhibition is on view in the third floor gallery, and it closes January 8th. So I encourage you to see the exhibition if you haven't already done so. It's my distinct honor and pleasure to introduce tonight's speakers. I was prepared to read their biographies, but they've requested that we dispense with a long introduction. Consequently, we decided to share their distinguished backgrounds in a printed program so that you know of their accomplishment and why we recruited them for a program focusing on innovation and invention. How many of you have never accessed the internet? Yeah, I think that demonstrates my point of how much of a profound impact the internet has had on the way we live and communicate. In moments of reflection, I often wonder how we do some of the things that we do now that we had done in the past without the internet. And it's really mind-boggling. You know, how would we make travel reservations, find a dentist or a repairman, or stay up to date on current affairs, current events that may have occurred in our neighborhoods across the country or even around the world. It's quite awesome, but our ability to receive this information would not have been possible without the internet and the efforts of the men who contributed to its development. Now we have an opportunity to hear about it and how it started. So without further delay, please join me in welcoming to the stage our Internet inventors, Dr. Stephen D. Crocker and Dr. Vint G. Cerf. Thank you.
Good evening.
Hi there. So thank you, Nona. Vint and I have been friends for something over 50 years, going back into high school. And Vint was the good student, and I was the one who got in trouble. And one of the ways of getting in trouble in those days was to go find the nearest computer because they were not so prevalent. And this was Van Nuys High School, which in the San Fernando Valley of Los Angeles. I got access to some computers at UCLA, and we were math geeks in those days, so I was exploring what turned out to be fundamentally uninteresting mathematical equations. And one Saturday, I dragged Vint over, we drove over the hill to UCLA, and I had permission to use this computer in the engineering building, but I didn't have any keys or anything like that. And the building was locked. And I was sort of crestfallen that we were standing there in front of the building and we'd driven all this way. And Vint looked up and saw that the second story window was open. And I thought, we're not really going to do this, are we? Next thing I know, Vint's on my shoulders. There's a casement window that, you sort of hand crank and it opens up. He went in, through the second story window, came around, big institutional doors with a big push bar, opened it up. We got some tape and taped the door so we could get in and out during the day, go to the cafeteria and buy lunch and so forth. Inside the building, everything was open and we had no trouble getting to the computer, and we spent several hours there. That was 1961 in spring. 11 years later, a similar institutional push bar door was taped open, and the plainclothes cop who came by and the Watergate was the lookout on the other side of the street at the Howard Johnsons didn't recognize the trouble that was coming. And so the Watergate burglars were arrested. And at that point, I was now working for the Defense Department, had a top secret clearance, and the shiver that went through the back of my spine was incredible. Several years later, we were back at UCLA for a celebration of we both had Jerry Estrin as our thesis advisor, and it was his 80th birthday, and the department was honoring him. There was a departmental meeting on a Friday evening, and then the graduate students got together for brunch with him on Saturday morning. The building that this little incident took place in was scheduled to be torn down. Vint and I looked at each other and said, well, we ought to recreate this break-in. Vint's famous for wearing three-piece suits. I said, we don't really need to be dressed up like that. My recall is that he said, I don't have anything else. One of our friends, who was by then a full professor, said, I'll bring the cameras. And so we met early the next morning on Saturday and recreated the incident.
And if I can have the projection system, please. There we go. This is the beginning of the recreation.
That window was still open. That's the exact same window, and it was still open.
After this little exercise was over, we sent a note back saying, your security is no better 40 years later than it was then. So here we've discovered the window again, and I'm getting help working my way over, and some additional help getting.
Vint is considerably more agile. I had what you might call a supporting role.
Here we go into the building, and out we go. And now, one thing, if you're paying close attention, this was a two-piece suit instead of a three-piece suit. I'm being a little bit more informal.
This is 8 a.m. Saturday morning.
So that actually brought back fond memories. The building is now gone.
And the statute of limitations is also gone.
Thank God for that. So you mentioned that you ended up at ARPA, and so this is an important thing. But let's go here, first of all. It's 1963. This is after Steve and I did our little thing at UCLA, but before we actually got involved in any of the ARPANET or Internet. A man named J.C.R. Licklider at MIT, who was a psychologist and not a technologist, believed that computers could be used for non-numeric purposes. And so he formed this little working group that he called, I don't think it's exactly readable, but it says, to members and affiliates of the Intergalactic Computer Network. And he apologizes for the delay in sending his notes around. This is 1963. He's talking about building networks to connect computers together so people can share resources. So that's sort of the beginning of the ideas behind what became the ARPANET. He became the first director of DARPA's Information Processing Techniques Office, which funded the ARPANET project, among other things. This is Steve and Vint at my wedding. He was my best man in 1966, and you can see we were both clean-shaven, young-looking fellas. Then the nice lady on your right is Sigrid, who's in the audience down here, my wife. This was 1968. I became her zoot at this point. And the guy in the middle is a family friend. Of course, he's passed away now, but you all recognize him. Then comes, I think, the idea of the ARPANET and what to do. A man named, the original plan that Larry Roberts, who led the project for DARPA, had was that all the computers that were had been acquired by DARPA for the computer science departments that were doing research on artificial intelligence and other computer science ideas would be used to connect together. They would be directly connected to each other in a network. Each one of those mainframe time-shared computers would run the networking software as well as all the other applications. But this fellow, Wes Clark, who was, at Washington University in St. Louis?
I think that's exactly right.
Is thinking, this is now in the late 60s, Digital Equipment Corporation has been formed. They are making the PDP-1 and the PDP-6 and the PDP-8 and so on. And these machines are getting less and less expensive over time. Wes has this brilliant idea. He says, why don't we just dedicate some small computers to be the communication devices, and we'll hook them together, then we'll have a nice homogeneous system. The software will be all the same. We don't have to have different software in every machine in order to form the network. So the subnet idea and the creation of what became called the interface message processors came out of Wes's idea to dedicate machines to build the network.
And it may be helpful to remember that in those days, mid-60s and late 60s, a typical computer had an uptime of measured in hours usually. It didn't last. It was very rare for a computer to stay up running for days on end. And so we were some distance away. These days you turn on a computer and you just leave it on. But back then,
Good point.
It rarely ran more than even a whole day without crashing and needing to be restarted. So it was relatively, it would have made a huge difference. I mean, it did make a huge difference. It wouldn't have worked the other way.
So this notion eventually was codified in the ARPA order for an interface message processor. As it turned out, a number of different parties competed for the contract to build this packet switch, this interface message processor. And ironically, by this time, Steve and I are now graduate students at UCLA, but we're working part-time for a company called Jacoby Systems in Santa Monica. Jacoby Systems bid on the ARPANET contract, and Steve and I, as sort of junior people in the company, participated in that. I remember doing a GPSS simulation of the network to see what its performance would be. We lost. Jacoby Systems lost the bid. It went to Bolt, Beranek, and Newman in Cambridge, Massachusetts. But since we were working at UCLA also for a guy named Len Kleinrock, who was an early pioneer in the analysis of packet switching networks, we got to work on the ARPANET anyway because he won the contract to build the Network Measurement Center. So by good fortune, even though our attempt to get the bid to build the IMPs didn't work, we still got to work on the ARPANET. There's a funny story about the award of the result of awarding the contract to Bolt, Beranek, and Newman in Boston. I don't know if you're familiar with the message. Would you like to describe what happened?
I think you're talking about the congratulatory note
Yes.
from Senator Ted Kennedy's office. So the protocol in some of these cases is the government awards the contract, but the appropriate senator or sometimes congressman will get informed. So Kennedy's office sent out a note congratulating them on the interfaith message processor.
Yeah, actually the language, what was particularly charming is the language said, congratulations on your ecumenical effort in creating an interfaith message processor. So obviously something has been lost.
It's not the only message to Congress that didn't get through quite as intended.
So the ARPA order is won by Bolt, Beranek, and Newman, and a number of now long-term friends of ours participated in that effort. What emerged out of the project was this incredible heavy-duty, heavy metal thing called the IMP that showed up on September 1st, 1969 at UCLA. All four of the original ones, we'll show you a little map of where they went, were delivered in this form with this heavy metal and even screw eyes on the top, hooks, so that you could deliver this by helicopter. I think the BB&N guys thought, well, it's for the military. We don't know where they're going to put it, so we'll prepare this for...
Actually, they weren't worried about the military. They said these were going into universities, and they were more worried Quite seriously, they said, we want these things to be ruggedized because we have no idea what's going to happen when we lose control of them and put them in these hostile
and all
environments.
these graduate students that are around,
Yeah.
they're more hostile than any military environment you can think of. So this is a photograph of the ARPANET IMP that was delivered in September of '69. I don't know whether you would like to recount your concern about the software not quite being ready on the host side to receive this particular machine.
Yeah, so the delivery date was scheduled, as you say, to be September 1st, 1969. We heard in mid of August that BBN, Breakin, was having a little trouble with a hardware glitch and that they were sorting out. I was responsible for trying to build some software at UCLA that would connect the computer we had at UCLA to this machine, and I was a lot more than a little bit behind in trying to get that going. So I was really quite pleased actually to hear that there was a problem in delivering the IMP. Further, I figured that they would deliver it, and then Honeywell people, where the box comes originally from Honeywell, Honeywell would send out a hardware guy to make sure it was working, and then BBN would send out a hardware guy to make sure that it was working from their point of view, and then they'd send out a software guy. So I figured that there was several days, if not a couple of weeks of
This is like Labor Day. So
yeah,
and
this is right around Labor Day.
Right.
But I miscalculated. BBN was absolutely determined to deliver on time. They ironed out their little glitches of the hardware, put it on an airplane, and it showed up 2 days before the end of August. And my 2 weeks of assumed slack,
time, right.
disappeared, and I was left exposed.
So the first 4 nodes of this ARPANET were installed 1 a month roughly. So by December or January of 1970, we had 4 nodes, one at UCLA, the first one, the second one at SRI International in the San Francisco Bay Area, the third one at UC Santa Barbara, and the fourth one at University of Utah. And this is the picture that was formed. There was generally one computer on each node. The telephone circuits, dedicated telephone circuits that connected each one of the IMPs was running at the blazing speed of 50 kilobits per second. Now, you have to understand, in 1969, this was considered broadband. And it was actually fairly hard to do. The device that turned the digital signal into an analog signal on the telephone lines was about half the size of a refrigerator. It was a Bell 303A modem that took 12 voice lines and bonded them together in order to get 36 kilohertz of analog capacity, which was then modulated to 50 kilobits a second. But that turned out to be very important in the design of the system, because the original idea had been to run much lower speeds, which would have made the system a lot less swift and less responsive. So the 50 kilobit circuits were actually something that contributed to making this a useful thing for both interactive processing and also fairly fast file transfers.
Before you move off of that, the other thing that I remember about this 4-node network is this, of course, is in the western part of the United States. There was actually a little bit of politics involved in the choice there. The ARPA designed this network and placed it in the sites that they were already supporting. So they were supporting research around the country.
Right.
And many of the principal investigators, the professors who were running research at these places, were not necessarily excited about having this network. Their view was, hey, we've got our computers here. Why do we want anybody else intruding, sharing, using our cycles, whatever?
Well, besides, you waste money on building a network that could have been spent on more graduate students. So
Yes.
they were, not happy about this whole thing.
So, and it turned out that there was, for reasons that are a bit subtle and maybe not too interesting, more resistance in the East than there was in the West. And so ARPA said, okay, we'll start this network in the West. And so this is why the first 4 nodes were chosen. Very rapidly, once it was going, everybody said, oh, when do I get mine? And that all shifted.
So actually, there are a couple of interesting things about the choice of nodes in addition to what Steve is describing. The UCLA node was there to run the measurements. I was responsible for programming all the measurements and the artificial traffic generators and everything else at Len Kleinrock's shop. UC Santa Barbara was very much interested in visual software simulations, things like they used the tectonics display.
The color-freed system was a very advanced
take complex
system.
equations and graph them so you could see what they looked like. SRI was particularly interesting because a man named Douglas Engelbart was there running what he called the online system, NLS. Don't ask me why it wasn't OLS, but anyway. This Engelbart was incredible because he and Licklider both resonated on this idea that computers could be used for something other than number crunching, and in particular, knowledge work. So if you haven't ever heard of Doug Engelbart, you should, because this man invents hypertext. He didn't necessarily call it that, but he had hyperlinking or linking between documents on a time-shared machine. He invented a mouse with 3 buttons so that you could point to places on the display in order to interact with documents that you were working on. He had a portrait mode display that made it look like a sheet of paper. He had black on white presentation instead of yellow on green, or vice versa. This was a tour de force, single computer World Wide Web, if you like. I don't mean to diminish anything that Tim Berners-Lee did, but this was a demonstration of what you could do in non-numeric processing. It was quite dramatic. And so it was an excellent place to cite what was called the Network Information Center, where information that was being generated through this online system would be accumulated and shared with other people on the network. And Utah turned out to be a major site of image processing experimentation and research. So this was actually quite a powerful set of 4 nodes. It made very good sense. And as Steve says, there was resistance on the East Coast.
Let me expand on that just a little bit and put some emphasis there, because here we are, we're graduate students at one of these sites, and we are all of a sudden interacting with other places around this advanced research community. And although we didn't have, the equivalent of smartphones in everybody's pocket, there were instances of things that were pretty far advanced for the time and gave us a very, very long look ahead. So as Vint said, Engelbart's shop, he had a mouse, keyboard, interactive graphics, linking of documents and so forth. And so if you were sitting there, you could do there a early version, but a very effective version of the same things that now everybody can do. And so we're talking about a 40-year leap ahead, and enormous looking into the future. And it wasn't just his laboratory, but each of the other laboratories, whether it was graphics or whether it was advanced architectures or whether it was big databases, there were instances of what has eventually turned into commonplace technology today that we were able to live in and sort of see far into the future.
This was, it was really a coup and an honor to be part of this community, because there were so many very smart people who were, as Steve says, pushing the envelope of what you could do with computing and communication. So I think the next slide here shows a bearded Vint and other colleagues in front of the Sigma 7 machine that was the first one to be connected to the ARPANET IMP at UCLA. Then we see the beginning of growth to the East Coast, but not too much in the middle in 1970. Now this is an important point that I want to emphasize, because Steve hasn't gotten nearly the visibility he should get for what he did. Here he is, he's a graduate student, and we're expecting the principal investigators and the guys at DARPA who are running the program are going to tell us, what it is they expect us to do and how to do it and everything else. And they basically said, here's the net, go figure out how to use it. So Steve grasps this nettle, starts the network working group, and issues a thing called request for comments. Now, you should tell them why you called it request for comments.
So in August 1968, before BBN has won the contract to build the IMPs, but after ARPA is committed to having a schedule and everything, representatives from the first 4 sites, the 4 that you saw, and got together. There was a meeting called, and every site was asked to send somebody. The heads of the projects at each of these 4 sites did not go. They delegated it downward to graduate students or secondary staff. Vint and I drove up to Santa Barbara where that meeting was. meeting was small. It was 6, 8 people, and we instantly connected with each other. It's sort of like a cocktail party phenomena where we could tell we were all on the same wavelength. And we made a couple of very important decisions. The first was that we knew we needed to keep talking with each other, and therefore we wanted to go visit each other's laboratories. And we knew, as we said that one purpose of this network was to reduce the amount of travel that was necessary to do research. And the first thing we did was schedule trips to go visit each other, the beginning of the boondoggles. We met intermittently over the next several months, kicking around ideas large and small. What were we going to do with this network? And we wanted to leave a lot of room, and so we were a lot of blue sky conversations. And in the spring, I could feel the pressure to get some of this written down. And so we made assignments to each other. We said, okay, you write up that idea you've been talking about, and you take that one, and I took one. And then I volunteered to try to organize those notes. And I found myself very nervous about that clerical administrative task, because it took me a while to realize it, but I was afraid that the act of writing down what we were thinking about would be interpreted as an assertion of authority. And we were just young kids. We were just graduate students. And further, we were on the West Coast, and all the authority was in the East somewhere. So I found myself really quite nervous about this, and also considerably under considerable pressure to do what I had said I was going to do, which was to organize these notes. So late one night, I couldn't sleep, and I was feeling a lot of pressure. I wrote a few sentences about what the rules for these notes were, and then to emphasize that they were not official, I said, oh, so here's a little linguistic device. We'll just, no matter what it is, whether it's complete or incomplete, or whether it's what's stated in, we'll make every one of these by formula a, quote, request for comments. And so, and I figured it was temporary, it'll last a few months until we had real documentation for the network. They're still going strong. I was asked to write...
There are over 5,000 requests for comments now, and many of these documents carry huge weight because they often specify the protocols that are used to make the internet run.
The early notes were very, they had things like mailing lists, and they had, one sentence sometimes.
Jokes.
Jokes. Over time, that got replaced by mailing lists on the net and by internet drafts and less formal kinds of things. And the requests for comments now are not requests for comments at all. They are heavy-duty, edited, formal documents.
Command directives. But this document was not an RFC, interestingly enough. This is what Steve undertook to do at the request of Larry Roberts, the guy who was running the program at ARPA, is to organize the network working group. And the problem here was that we needed software that was compatible between every single computer in the network that is attached to the subnet, to the IMPs. So these are different machines with different operating systems, different word sizes, all kinds of variations. And yet somehow they have to be able to send information back and forth to each other through this common network. So the first problem to solve is, how do you do that? How do you get machines to talk to each other in spite of the fact that they have different word sizes and different operating systems and everything else? So that was the first thing that Steve tackled, was leading the network working group to develop this host-to-host protocol. This document was called document number 1, and it wasn't an RFC because this was not a request for comments. This was a description of what the procedures would be for these computers, and the people who were programming them were supposed to make the system behave the way this document described. So this was a major step in the direction of creating a useful network. There were many other similar kinds of documents for other kinds of protocols, like people getting access, remotely getting access to time-sharing systems or transferring files from one machine to another. They were all either host protocols or application layer protocols or utility protocols. But Steve gets huge credit for organizing and leading this activity in a way that was extremely open, and it invited...
Thank you very much.
Yeah, thank you. That's good. You were supposed to do that over dinner. What's important is that Steve found a way to do this that was very inviting for all of the other 13 or 14 different universities that were participating. Anybody with a good idea was welcome. And if nobody else liked the idea, it didn't go anywhere, but you were free to try. So request for comments and implied invitation to participate was really a fundamental social atmosphere that Steve's leadership created. To say nothing of the incredible groundbreaking invention of this protocol in an environment that it had never been done before. What had been done before was that specific machines from particular manufacturers might have been interconnected to each other in a more uniform way, but not this gangrel collection, this zoo of different machines communicating with each other through a common net. Now this is Steve at DARPA. You'll notice that he became more hirsute in the process of going east. And the man who is giving Steve a certificate is the director of DARPA, a man named Steve Lukasik. Steve, when he came to DARPA, was responsible not for the ARPANET project anymore, but for artificial intelligence. But you might explain what the reaction was at DARPA to having this unkempt person showing up with a top secret clearance.
Yeah, so this is this picture is a little later, but so I was at the agency was first called ARPA, and then it got renamed DARPA. From mid-71 to mid-74, the Vietnam War was in high gear. Demonstrations were taking place regularly on the streets of Washington as well as around the rest of the country. So I was in disguise with long hair and beard, but with no real commitment to that. It came about because my sideburns kept going up as I lost track of where I was supposed to shave. So one day I said, well, let's let it all grow. And it was serious, it's true. And in those days, my beard grew very quickly. And while I was in that couple of week period, I realized that as I walked down the street, I was getting different reactions than I had gotten before. Policemen looked at me a little harder, and women looked at me a little longer.
Did anybody give you any money?
Thought, well, that's huh?
Did people give you money?
No, nobody gave me money.
Homeless?
No, it didn't work that well. But so I just let the beard grow, and I figured, oh, I'm coming to Washington. I'm working in a serious, real adult environment, and everything's going to be buttoned down. And so I was fully prepared to shave the beard and cut my hair. But there was instantaneously when I arrived, I could tell a kind of reverse psychology. I'd walk into a room, and I could tell that I had much higher credibility because I couldn't be there because of my looks. It must be that I knew something. and it's funny, and I tell it as if it's a joke, but I can tell you it was really true. And so I said, okay, well, I'll just go with it.
Amazing. Yeah. Unfortunately, I don't have a photograph of Steve getting married to Beth in 1974, but he lost the hair about that time. This is what happens when the ARPANET is now in operation. It's been running since 1969. Protocols have been implemented. It's been demonstrated publicly in October of 1972. And a friend of mine who was at that time running USC Information Sciences Institute, Keith Unkefer, and I took the road show to Johannesburg, South Africa, and I helped him demonstrate the ARPANET to our friends in South Africa. This turned out to be a fairly complex operation. If you'll notice in the background there's a telephone plugged into a thing called an acoustic coupler. This is back in the days when you weren't allowed to make any direct electrical connections of any kind to the network, so this was basically a computer literally talking in analog form into the telephone network. But this was a foreign device, and from the standpoint of the South African Telephone Company, this was a thing that they were not going to allow to be connected to their network for fear that it would damage it. So there was a protracted interaction and debate on this subject. We finally got them to agree, and I demonstrated the ARPANET chess-playing programs and a bunch of other things using this fairly early terminal. So now the ARPANET is continuing to grow. By this time, it's covering quite a large amount of territory, and although it's not obvious, some of the ARPANET has extended itself into Europe. a satellite link had been acquired and shared with a seismic array that was based in Norway. That seismic array project was a DARPA project to detect nuclear explosions in Russia and try to assess what their yield was to make sure that they didn't exceed the test ban treaty limits. And Bob Kahn, whose name you haven't heard yet, who was very much involved in the ARPANET design, by this time has been at ARPA for, by this time, 5 years, negotiated to get some portion of that circuit for the ARPANET to use. In fact, they doubled the speed of the circuit from the blazing 4.8 kilobits a second to 9.6 kilobits a second, so they could do packet switching over that link. So by this time, the ARPANET has extended into Europe as well as Hawaii and the continental United States. I don't know whether you have any particular observations about that state of affairs.
I'm glad you mentioned Hawaii. I was going to mention that because that was another satellite connection in the other direction. A small historical footnote, the guy who was running the US side of that link was a guy named Rick Adams, and then went on to found UUNet that got absorbed by MCI, that got absorbed by WorldCom.
It was absorbed by MFS, which was absorbed by WorldCom, and then which acquired also MCI, yes.
Yes.
And then went bankrupt.
And,
and Mr. Evers is in jail, which is where he belongs. Okay, go ahead.
Rick made out okay. You went to work there for a long time. And,
yes, I was at MCI for a long time. Rick sold his UUNet internet service, which is a story we haven't quite got to yet, for about $2 billion, and then retired to go do something else. So here we are. It's 1977. Meanwhile, we're celebrating later on in 1994 the 25th anniversary of the ARPANET's initiation at UCLA. And here you see a carefully crafted shot from Newsweek magazine. We must have spent 8 hours setting up this shot. The guy on the far left is John Postel, who was at UCLA also, along with Steve and me, way back in the late 60s and early 70s. He was in charge of curating the RFC series and managing the names and the numbers of the ARPANET and then the Internet as a project. Steve, as you already know, was deeply involved in running the network working group, and I just sort of tagged along in all this to try to be helpful. But what we did here was to build a primitive networking system out of yellow squash, green zucchinis, and some yellow copper cable, and coffee tins. And it took us a while to assemble all this stuff. Then we had to draw all these pictures of the ARPANET and the linkages and the sheets of paper. So 8 hours later, we're ready for the shot. And I want you to notice how we set up the network. It couldn't possibly work. This was a geek joke that we hoped some people would get. You'll notice that it's ear to ear and mouth to mouth. There's no mouth to ear anywhere. There's no way this network would ever work. And it was mostly just to illustrate how primitive networking was when we first started doing this stuff at UCLA.
And how unobservant the editors were.
So I'm sorry to say, now John was an amazing guy. He was our resident hippie. He wore sandals and had long beard, long hair. But he was incredibly good at archiving things, at documenting things, at keeping track of things. He became first the numbers czar and then the Internet Assigned Numbers Authority, managed all the domain name system, managed all the allocations of Internet addresses. And so at the ITU in 1996, he got the silver medal for his contribution to networking. Sadly, a couple of years later, John passed away, just as the Internet Corporation for Assigned Names and Numbers was being created. And that's a whole other story, which we don't have time to do right now anyway. Because I'd like to move into the Internet, because that hasn't happened yet. In this whole story, we've been talking ARPANET primarily. So Bob Kahn and I begin work in 1973 on this notion that maybe we should be able to build more than one packet switch net and hook them together. And there was a rationale for why that might be necessary. oh, this is me at Stanford University, and when I still had a little hair and my beard wasn't white. Bob and I began talking in the spring of 1973 about the possibility of using mobile radio, using satellite, and the original ARPANET wireline system as an ensemble for introducing computers into command and control. If you think about it, it works fine to have the computers hooked up by telephone circuits, but if you try to attach wires to the tanks and the tanks go around and they run over the wires and it breaks, and if you try to tie ships at sea together with wires, that doesn't work either. So you need satellites for ship to ship and ship to shore, and you need ground mobile radio for mobile operation, but somehow all of them are still packetizing everything, and they have to be hooked together. So that was the internet problem. How do we hook them together? So Bob and I wrote a paper in 1973, which was published in 1974, about how to connect things together. What was the design of the internet protocols that would allow this to happen? Ironically, this was published by the IEEE Communications, Transactions on Communications in May of '74. A copy of that transactions publication was sold at auction 2 years ago for $35,000. So I immediately went to my filing cabinet to see if I had any more of them. And I'm sorry to say I didn't find any, so I have to come up with a different retirement plan. But this document was created in the context of all the things that Steve had described, the things that were going on at SRI, the things that were going on at all the other sites around the ARPANET by 1973, and Xerox Palo Alto Research Center, which is 1.5 miles from my laboratory at Stanford University. So, and in fact, Steve can claim some other incidental credit. Bob Metcalf is the guy that invented the Ethernet. He did so while he was at Xerox PARC. But he doesn't do this until he's at Steve's place in Washington and sees a paper by the guys at the University of Hawaii on something called the Aloha Net. This was a network of actually taxi radios that had been repurposed. The terminals had these little taxi radios in them, and you would type something, and as soon as you finished typing a line and hitting a carriage return, the repurposed taxi radio would transmit from wherever you were to the University of Hawaii mainframe. Actually, it went to a machine kind of like the ARPANET IMP, except it was called the Menehune because that's Hawaiian for imp. So this it's true. So the reason they called it the Aloha protocol is that the way it worked is that all these various terminals could transmit at any time. And so they could potentially collide. So Aloha is sort of you do it whenever you want to. So if they collide, you figure it out because the guy on the other end doesn't get it and he doesn't send you an acknowledgement back. So then you have to retransmit. But the whole point here is not to retransmit exactly at the same time later because then you'll keep colliding. So instead, you roll the dice for a little while and you randomly retransmit. So the Aloha Net was a random multiple access network. So Metcalf looks at this and he says, that's cool. And he goes to Hawaii and he comes to Xerox PARC and he says, I can do this on a piece of coaxial cable at 3.3 megabits a second. So he invents the Ethernet along with David Boggs. And that, so this is a stunning thing. And he wouldn't have done that if he hadn't seen that report.
He was, when we were building the ARPANET in the early days, we fell into an each one teach one kind of mode of operation. And so the graduate students who had experience helping putting their own systems together, we rounded them up and gave them lofty titles called network facilitators and sent them off to go help other people who were going. And so Metcalf was one of these very, very bright kids working at MIT, and he was actually a graduate student at Harvard. So forward a couple of years, he's now at Xerox PARC, and I'm in Washington, and he comes over and he stays at my place. So I put him up on a sofa bed. I think he's resented ever since that it wasn't a real bed. But I had on my coffee table this paper on the Aloha network, and I said, this is pretty interesting stuff. You ought to take a look at it. So he stayed up, he read that thing that night, and he said, the math here is all wrong. And he got really angry. I remember reading this thing, and he said, this isn't the way you should do it. And as you said, that eventually eventually was pretty quick actually. He said, I can do this in a cable and we can make it symmetric, and so that was the birth of the Ethernet. First at 3 megabits a second in fairly fat cables, and then eventually to the 10 megabit standard that became the commercial one. So I have the unique and singular honor of being the host of the father of the Ethernet.
So to come back now to Bob Kahn's problem, which is how to get the computers into military command and control in a networked way, he began a project called the Packet Radio Net using mobile radio. Now, these radios were pretty dramatic. They were about a cubic foot in size. They cost $50,000 each. And they were using some of the most advanced and at that time almost classified technology called CDMA, or Code Division Multiple Access. That's what Qualcomm now offers in people's mobile phones, but this is 40 years ago and extremely advanced, running at between 100 and 400 kilobits a second. So SRI International was the systems integration site. The people who made the radio were at Collins Radio in Texas. And they put the radio repeaters up on the tops of the mountaintops in the San Francisco Bay Area, had repeaters on the buildings, and of course mobile equipment. And so we would drive around in the Bay in these mobile vans in the Bay Area, testing the quality of the network and the ability of the TCP/IP protocols to actually work in this fairly potentially noisy environment. There's a story about the engineering guys who would drive up and down the Bayshore Freeway, and occasionally they'd pull off to the side, and the driver was one of the engineers, so he went around to the back, and they had all of this measurement equipment and test equipment and traffic generation equipment and everything else. So one day, the story goes is that they were parked at the side of the Bayshore Freeway, and a police car comes up, and he sees there's nobody in the front, and there's this completely unmarked van, you know, with a big antenna sticking up the top. So, you know, he knocks on the door, and the door opens up, and he sees all these geeky guys with, you know, computers and displays and radios and everything else. And he said, who are you? And the guy in the van says, oh, we work for the government. And he says, which government? But officer, we were only going 50 kilobits per second. So what was particularly amusing about all this is that I would occasionally go out there, inherited the responsibility for the program when I went to ARPA, and I would take the military out to drive around and see how this stuff would actually work. In the inside, you see these white things in the middle of the screen. Those are the big packet radios, the $50,000 gadgets. But what is particularly interesting is that even then, in the early 1970s or mid-1970s, we're experimenting with packetized voice. So the thing that you use on your laptops now, things like Skype or Google Talk or any of the iChat and so on, are things that we were trying out, of course, in a much less communications-rich environment. In fact, because the backbone of the ARPANET only had 50 kilobits a second, and the transmission rate in the packet radio system was on 100 to 400 kilobits, you couldn't get very many voice channels through these things, because a typical voice channel was 64 kilobits a second. So we had to use algorithms for compressing the data rate that was required to deliver the voice. And one of these algorithms was called linear predictive code with 10 parameters. What this did was model the vocal tract as a stack of cylinders whose diameter was changing with time, and it was excited by a formant frequency. So you could compress the voice signal down to 1,800 bits per second. So you could get a number of voice channels even through a 50 kilobit system using this method. Now there was a little problem though, because anybody that spoke through this system sounded like a drunken Norwegian. And the day that I had to demonstrate this to a bunch of generals over at the Pentagon, I remember thinking, how am I going to do this? Well, you remember that the Norwegians were part of the ARPANET project in Europe, and one of the participants was Ingvar Lund from the Norwegian Defense Research Establishment. So what we did was we got Ingvar to be the speaker, and he spoke through the telephone system, and it's, you know, and then we had him speak through the packet radio voice system, and it sounded exactly the same. We just didn't tell the generals that everybody would sound that way. But I think the important part here is to recognize how long ago many of the ideas that we now take for granted were beginning to take shape and were considered very much experimental at the time. The same could be said for the satellite network. We used Intelsat 4A and had multiple ground stations in the US and Europe using Aloha methods as if you had an Ethernet in the sky. And it was those three networks, ARPANET, the Packet Radio Net, and the Packet Satellite Net, that were interconnected for the first time November 22nd, 1977. And I was at ARPA at that point. And I have to tell you, this was one of the most exciting moments for me because it was the first time that we connected all three networks up using the TCP/IP protocols. And it was a carefully crafted demonstration because the packet radio van is going up and down the Bayshore Freeway, and it's radiating packets that go through a gateway into the ARPANET. The gateways are carefully adjusted so that the traffic leaves the packet radio van. It's supposed to go down to Marina del Rey, California, 400 miles away. But the routing is done so that it goes all the way across, out of the packet radio net, all the way across the ARPANET into the European part of the ARPANET, down to University College London, out another gateway into the packet satellite network and back down to the eastern part of the US, through another gateway back into the ARPANET again and all the way across to USC ISI. Now, the packets effectively went 400 miles. But if you look at the actual path, it was about 100,000 miles. And it worked. And you can just imagine, we're all jumping up and down. It works, as if it couldn't possibly have worked. That's software. I mean, it couldn't possibly work, but it did. So this was one of those great demonstrations where all three networks were able to interconnect using the same set of protocols. What was important from my point of view is that you could make any pair of networks talk to each other if you put some funny box in between. But getting all three of them to talk to each other in a uniform way was a big deal. And so this was an exciting moment in my story, anyway, of
one of the challenges in this business is what's called tech transfer. And Vint's story about the 100,000-mile path for the packet is it tells you why the tech transfer process is not very good. The airlines give you that kind of routing now when you try to buy a ticket and you only want to go 400 miles.
Actually, the airlines do something else, which is even more interesting. Have you ever gone up to the ticket counter? I watched one guy go up and he says, hello, I'd like to buy a ticket to Paris and I'd like my luggage to go to Istanbul. And the ticket agent says, oh, I'm sorry, sir, I can't do that. And he says, I don't know why not. You did it last week. This, I don't know if you can read this, but there's a bunch of nerds that are out there looking like they're in the hayfield somewhere, and the text says, stay downwind and back away slowly. The last time I heard of these things got spooked, the internet got created. So that's what really happened. So some of these are charts that I stole from Steve. This is a picture of how many users are on the net up till 2005. Now we know the numbers are on the order of 2 billion or more.
Yeah, and I stole these slides from Scott Bradner. So.
Oh, okay, so it's his fault. What's actually interesting about the numbers is that it really isn't clear anymore how many people are on the internet, because the 2 billion number, which is kind of approximated by surveys and things like that, is probably now dominated by the fact that there are 5.5 billion mobiles in use around the world. Some fraction of them are internet capable, the smartphones, and that's at least 15 to 20%, maybe even 40%. Eventually it'll be 100%. And so the number of users of the internet capability, even though some of them may only be getting there through mobiles, is bound to leap up to very nearly all of the world's population somewhere by the end of this decade, if not sooner.
So this is one of my favorite slides. The previous slide is the traditional one that shows exponential growth in numerical terms, quantitative terms. This is a kind of notional slide about which sets of people became aware of the network over a period of time. And Tom Brokaw on NBC TV, 1988. And then it ends with a picture of Scott's mother as as a sort of the idea that every grandmother now knows about it. I tend to think of that as more like my mother-in-law, who once threw me out of the house because I tried to bring a terminal into the room, into her house, in what may have been the only tense moment in the roughly 40-year relationship we've had. But some years later, not very many years ago, we gave her a laptop, and she took great delight in stealing the Wi-Fi signals from her neighbor. and our relationship has warmed considerably. She treats me a lot better now.
So then comes the dot boom. I was fond of running around saying IP on everything. Of course, the whole point was that when the basic design of the internet was being done, Bob and I recognized that we didn't know what new communications technologies would be invented after we had standardized these protocols, and we wanted very much for the internet to be able to absorb any new communication capability that might come along. And so the IP on everything was to sort of indicate that. Of course, it also had other implications. So the internet explodes. This is a picture of the internet in 1999. It looks the same way, except bigger and more colorful now. But what's interesting about the picture, and the thing that I'd like to emphasize, is that the different colors represent what are called different autonomous systems in the network. The network is made up of hundreds of thousands of different independently operated networks. It's an entirely voluntary system. It is completely distributed. Nobody is, literally, no one is in charge. No one is forced to do anything. No one is forced to interconnect. They interconnect because it's useful to do so. And in the cases of commercial operators, it's useful to their customers. But not everyone is a commercial operator. Some of this is not-for-profit. Some of this is government. Some of it is commercial. Some of it's at home. Every one of us with our little Wi-Fi networks are running a little piece of that picture. So the thing that is interesting about this is that although a lot of it was motivated by wanting a very distributed system with no central control and therefore no weakness or vulnerability, it is a reflection of what Steve started with the Network Working Group and this notion of inviting people to participate on a voluntary basis. And I think that theme and that atmosphere permeated not only the ARPANET project, but the internet even today, despite the fact that there are lots of tension right now about governments that want to suppress people's ability to speak and other issues and arguments over net neutrality and things of that sort. There's still, in the core of all this, a highly collaborative and highly cooperative environment.
I suspect you could go on for
A
quite a
million
long
years.
time. I was noticing that we've been here for the full hour plus.
Yeah. So maybe we should stop and let people.
Yeah, maybe it's
ask
time
questions.
to encourage some questions. So this is a request for comments or questions.
Okay, there should be mobile microphones floating around here for people to use. There's a hand up way in the back.
Thank you both so much for an absolutely fascinating conversation and the opportunity to be a fly on the wall while you all discussed the development of this. I'm very curious to hear your thoughts about the implication of the app for accessibility to information on the internet going forward, and whether you think that this new notion of the application, which packages information in certain ways, will have significant impact on how we use the internet going forward, and whether it represents some sort of a paradigmatic shift.
Well, we actually did all that right from the beginning. We could see that these networks were going to be slower than you'd like, slower than the machines that if you were directly connected to them. So in that very first round of ideas that we sketched out, one of them was that the first thing that might happen is that you download some software and it would interact and do some things locally and some things remotely and try to reduce the amount of traffic that would have to send. That's morphed over the years, and now the current incarnation are these apps. there's a lot more to say about apps. I mean, from a cognitive point of view, how many of them can you keep track of? How many of them, really are important to you? And then there's a kind of long tail of other ones that you might use. And then there's thousands, hundreds of thousands, millions probably of apps that you've never heard of and don't want to use. I don't know. It depends sort of how close you are to it. If you step back and look at it from a broad perspective, it's pretty ordinary evolution. And so it's hard to get too excited about. But get your hands on a really sexy app, boy, that really makes your day.
So I actually have a slightly different take on this. First observation is that the value of the app in the mobile is realized primarily because the app is able to get from the mobile to the internet, to some service on the internet. And so it is the linking of the mobile to systems on the internet that provides value. So the app is an avenue for that. Second observation, and one which, again, in a way is like the RFC invitation, there's a platform there on each of the mobiles that invites other people to invent applications. And this notion of platform and application programming interface, which we use also at Google, is what allows a lot of creativity to happen without worrying about a lot of underlying details. The browser is a similar thing, and in fact, one of the most interesting observations for me about Tim Berners-Lee's browser work and invention of the World Wide Web is that the browsers that were built, Tim's and then later the Mosaic graphical version that Mark Andreessen and Eric Bina did, had the property, which all browsers still have, that if you're curious about how that web page was constructed, you can ask to show the source of the HTML or XML code that produces that web page, and then you can copy that and manipulate it and try different things out. So the job of webmaster, which didn't exist until the World Wide Web became more popular and visible, was almost self-activating because people could learn from other people by looking at what their browser code looked like. So this, again, this ability to invite people to participate and to create, to sort of mutually reinforce the infrastructure with new and creative ideas, I think is incredibly powerful. So I'm seeing apps as evidence of that sort of thing. Okay, let's see if we get the one in the front here. We got two, so we'll get the gentleman in the blue shirt. They're both blue shirts. How about the dark blue shirt is number one and the light blue shirt is number two? How's that?
So I'll just re-emphasize what was said before. Thank you very much for this talk. It was very informative to get an overview and fill in a lot of the holes in my technical knowledge about the development of the internet. I have two questions. One is very simple. Is it possible for us to get a copy of those slides?
Yes, certainly. I'd be happy to. You have a PDF already, so
Yes,
however, how does that work?
I can get your information.
Excellent.
Okay.
My second question, particularly your work as a grad student myself, your stories from those days are very inspiring. In fact, what I'm working on right now is a thesis to explore the relationship between the technical development of these technologies, in particular from the user HCI perspective, and the resulting policies. And I was just wondering what your thoughts on that relationship might be and how I might be able to research more information.
You go ahead.
My first problem is I wasn't able to hear all of the questions. So
how do you research the relationship of technology to policies?
Oh my goodness. Okay.
Is that the essence of it?
The technical details.
Well, okay. So
I think he got it.
So actually, maybe the broader question is not just technology and politics, but technology and society and sociology, and what happens when we're exposed to new technology? I was at a lecture at the Smithsonian last night, and it was about cyborgs, and there was some discussion about artificial limbs, for example, which ARPA has recently done some incredible work on to help recover functionality. And I remember thinking at the time that there were people who say, well, that's a terrible thing. It's not, the human body wasn't designed to have an arm like that is able to lift 6 tons. And I remember thinking, I wonder what people thought when they started making these little stone gadgets, you know, to chip them into stone knives and axes and stuff. Did somebody over there say, this is ethically bad because people don't have those in their hands normally anyway, so now you're exceeding the bounds of human something or other. So I think people, we're tool makers. We are tool-making animals, and we naturally gravitate towards things that allow us to do more than we could do before. And the computers have the interesting property that they help us with our wetware. They reinforce our wetware in the same way that electrical motors reinforce our muscles. So I'm not surprised at all to see this rapid influx of technology into the political and social realm. You can see it with social networking. You can see it with people trying to communicate with each other. The most amusing thing to me, having lived here for 35 years, is to watch the politicians first recognizing that this is an avenue for getting their ideas out to the electorate. That's the first reaction is, oh boy, I don't have to wait for the media to do anything. I can put up my own web pages. I can do all these things. What they didn't realize at the outset was that it was a two-way medium and that their constituents could come back and say something to them about what they thought. But setting that aside, there isn't any doubt in my mind that these kinds of mechanisms that allow voices to be heard that might not otherwise be heard is incredibly powerful. We see it in the Arab Spring, and I'm sure we'll see it more in the future.
Let me give maybe a less exciting view about the interaction of technology and policy issues. When I hear discussion about policies, to me that means that there are value systems coming into play, and almost always, whether it's made explicit or not, a question of who's going to get what they want at the expense of somebody else who doesn't get what they want. It becomes a trade-off of some sort, either economical or otherwise. I'm now forced to sit through numerous policy discussions, and a lot of these policy discussions are people whose trade and education is in policy space, and they have very little basic education in the technology. And so I walk into these meetings and find myself a little unnerved because there's no connection with what the reality is, or at least my view of the reality. So I've taken to try to socialize the following idea, that the policy people should try to frame their question. And then they should bring in technical people who can tell them both what's possible and what's not possible, because very often these policy discussions will have assumptions built in that this is not possible, and you can't have this and that, and therefore you're going to have to trade off. And sometimes they underestimate what's possible. Sometimes they overestimate what's possible and say, well, just make it do that. And in fact, you can't make it do that because that's not the way things work. So, the process that I'd like to see is that the policy people sort of frame their question. They bring in technical people who then tell them both what the limits are and what the possibilities are, and give them the space to operate in, and then bring it back to the policy people who then, within that space, pick the point they want. So I've been calling this my Oreo cookie model, and the sweet filling in the middle, of course, is the technical stuff.
Can you bring this gentleman here?
Oh, I'm sorry, this gentleman over here with the light blue shirt was next, actually. We gave him number 2, and this is number 3, so if you hang on over there. Sorry about that. Yes, sir.
Thank you. I'm interested in how the innovative research that led to this was selected. For example, how, what was the process, and how did ARPA first identify and select this for funding? And then some other key points were such as when Xerox or some other key points that really led to this, how that funding was identified and selected, what the process was, and if it hadn't been selected, what might have happened. So.
Oh boy. We we put a great store by transparent, competitive processes, open access. None of that actually took place. The Russians put up a satellite, the first one, Sputnik, and that sent a shockwave through the U.S. government. And within very short order, the government said, we don't want to be caught short again. The Army and Navy had been warring with each other and had separate space programs. And this agency, ARPA, was created very, very quickly with a mission of preventing technological surprise. And it was placed inside the Defense Department, but outside of the Army, Navy, Air Force, and reported directly up to the Secretary of Defense.
By the way, its initial job was get us into space.
And the first thing it did was gather the pieces of the space program, and NASA was part of what was spun out of all that. And all of this is history that you can read quite authoritative books on. One of the pieces that, although it's well documented, isn't, I don't think, widely appreciated, is that the agency was given enormous latitude. A lot of the normal processes for deciding what to fund and how to fund were short-circuited, and the individuals who were in place in the agency were given authority to essentially say, I select this, and I want this person to do this, and this is what our program is. There were some checks and balances. It wasn't completely unconstrained, but it was far, far less bureaucratic than all of the other agencies that existed before and after, actually. So that was the late 50s, 50, 58, 59, and so forth. Vint mentioned the Information Processing Techniques Office that Licklider was the first director of. That grew out of an emphasis on command and control technology, and that office was created by the powers that be, by the senior management there, who said, yeah, we ought to start focusing some attention on this newfangled computer stuff. And there's lots more to say, but Licklider said, let's go build centers of excellence, high points of research. And MIT, Carnegie Mellon University, University of California, Berkeley, Harvard, a lot of key places he plowed a lot of money into. And very, very smart people started to work on fairly advanced problems with a fair amount of latitude. And then the question is, well, how do you select? Because there's always people who want money, and you only have so much money. And so that becomes a question of taste. And there's no perfect formula for that. One man's taste is another man's total disaster. Why are you putting money into that? In fact, just to go back to this network business, there were people who said, why are you building this network? The papers have been written. We understand what would happen. Don't waste the money actually doing the demonstration. Here we are.
So actually, I want to make a couple more observations about DARPA, because even though the bureaucratic component of this business has gotten a little bit more dense, they are still doing stunningly interesting work. And it's because they choose really hard problems that have the feature that they may have a low probability of success, but if they work, they have huge payoff. So the former director, a guy named Tony Tether, started what he called the grand challenges. And one of them was, for example, to get a car to drive itself in a 127-mile circuit in the desert. The first year they tried it, all of them fell off the road about 7 miles down the path. The next year, 7 of them made it all the way to the end, and the Stanford one won, which is, hooray for Stanford. The next year, Carnegie Mellon won. And the next, not very long thereafter, Google hired all of those guys. And now we have cars that have driven 140,000 miles in San Francisco on their own without running into anybody or running over anybody or running into anything. Now, we always have a driver in the car just in case, because legally can't do that. But we did ask for a law to be passed in Nevada that allowed these cars to drive on the road by themselves. I don't know whether that passed yet or not, but there's a lot of open space in Nevada, so probably wouldn't run into anything bad. But the idea of a grand challenge is pretty amazing. The most recent one from ARPA is the 100-year spaceship. Here's the problem. How do I get from here to the nearest star in less than 65,000 years, which is the best we could do with today's propulsion? So the challenge, which has been announced now, and there are people writing up their bids on it, is to figure out how to get to the nearest star system, about 4.2 or 4.4 light years away, in less than 100 years. And by the way, you have to stop, go into orbit as opposed to zipping through at 0.2 the speed of light. So that problem number one is propulsion. Problem number two is, after you get there, how do you know if it got there? You need to be able to signal back. And getting a signaling system that would actually transmit over 4 light years is some trick, especially if you don't happen to be, bringing hydrogen bombs with you or something. So I'm not sure what the outcome is going to be, but it's an example of really pushing the envelope to see what happens. They've done other spectacular work, like the stealth program, and artificial arms and limbs and things of that sort. Well, anyway, so the place is driven by high risk and high payoff, and that's how they select a lot of what they do. Okay, sorry, long answer.
Question over here?
Yeah, my question is, I would like to know if the two of you are on Facebook. And I ask that because I'm very interested in knowing, is when you were originally developing the internet, whether you had any notion that this medium would become so pervasive for everyday people in their everyday lives, particularly when originally it was really designed for scientists and academics, and even Berners-Lee had the same idea, that making the web available for specialists and people who use computers on a higher order. But nowadays, it's so pervasive, and I'm just curious whether you ever could have imagined that it would be used by so many people.
I didn't understand what you said. You said Facebook, what's that?
So,
Like Google Plus. We get asked questions like that a lot. Did you understand what was going to happen? Could you see? How much did you know about what was going to happen? That's sort of the question that comes up. I think each of us has slightly different answers, because we were all, we didn't talk a lot about it, but we were in it. As we've discussed, quite a lot of the technology that we use every day today, mouse, hyperlink text, even voice over the network, we had pretty clear visions of and instances where it was working. So this wasn't fantasy or science fiction. It just wasn't as ubiquitous. So we could see pretty far down that path. Speaking just very personally, I had not quite appreciated the miniaturization and the full effect of Moore's law and therefore the ubiquity of computers. So I could see that every institution, every business, every university and so forth would all be interconnected. I didn't quite see that everybody's grandmother and grandchild was going to be using it. It just wasn't as evident as that. We had the bare beginnings of social media with things called the finger protocol, so you could see where people were and you could chat with them, and there were social relationships emerging on the network virtually from day one. So the pieces of this, the scale, of course, is considerably different now, as you point out. Did we predict Facebook per se? No. Did we predict social relationships? Absolutely.
So actually, I think there's some concreteness. First of all, I do have a page on Facebook. I don't use it a great deal, to be honest, but I did try an experiment. I decided to say yes to everybody who wanted to be a friend, just to see what would happen. And so eventually I was getting email from people saying, well, I tried to friend you on Facebook, and I got a note back saying, Vint Cerf has too many friends. And so I took this as a personal insult, and I sent a note off to Sheryl Sandberg, who is former Google, but now the COO of Facebook, complaining that they had insulted me mortally and that they needed to do something about that, so I think they changed the number for me. So now I have 10,000 friends, and I don't care about most of them. So, this is like the kid that goes to camp, and he writes home and he says, Dear Mom and Dad, I only have one friend here at camp and I hate him. But it was an interesting experiment. I think Steve is correct, though, that when email came along around 71, 72, there was almost instant recognition of the social implication of that medium, because within a few weeks, there were mailing lists that were created. One of the first one was called Sci-Fi Lovers, because look, it's all geeks anyway, they're working on this stuff. And then the next one was Yum Yum out of Stanford, which was a restaurant review distribution list. So it was very clear that this was a medium that people would use to communicate with each other, in addition to using these machines for various and sundry kinds of applications. The story isn't over yet, because the next big wave that's coming is what the Europeans sometimes call the Internet of Things. These are devices that are on the network, whether they're sensor networks or appliances of all kinds. They're all becoming increasingly Internet-enabled. And I think I even have a picture of one of these things. Well, here's a bunch of them. These are just examples of things that are on the net now that we would not have anticipated being on the net, like refrigerators and picture frames and surfboards. This guy has got an Internet-enabled surfboard. He was out on the water waiting for the next wave, thinking if I had a laptop and my surfboard, I could be surfing the net while I'm waiting for the next wave. And I used to tell jokes about Internet-enabled light bulbs, right, until somebody sent me an Internet-enabled light bulb. It's an LED display. It's in the lower left here. It's an LED light bulb that probably lasts about 15 years, and it's got an IPv6 radio, 6-low-pan radio in it, so you can remotely control the light bulb, check its state, and do everything else. And I even have a sensor network in the house, which is sampling temperature, humidity, and light levels every 5 minutes and storing it away in a server down in the basement. And this is actually turning out to be a useful tool, because it's telling me something about how well the heating, ventilation, and air conditioning system is actually functioning. So it's not anecdotal. This is engineering data. And I think a lot of us will benefit either directly or indirectly by knowing more about how we use energy in our environment. So all of that stuff is emerging out of this network environment, and there's still lots more to come.
Your comment about the sci-fi mailing list goes back to the question about policies. There was active discussion at the time whether or not it was appropriate to let that mailing list exist on the network, or whether that was an inappropriate use of the technology. So just one of the early policy discussions.
Oh, there was a small nuclear explosion while the then director of IPTO, who was in London, Colonel David Russell, when someone from Digital Equipment Corporation sent out on a mailing list a job advertisement. And this created literally, we heard the bomb go off in London while we were here in Washington, because this was a completely inappropriate use of a government-supported network and experimental system. Of course, today we get all kinds of advertisements. Okay, a few more, and then we probably have to wrap up.
Go ahead.
Here we go.
I can't help but wonder, surfing the internet, the whole phrase, is that connected to the last name being Cerf?
That's question number 272. So the honest answer is no. What happened is, although there is a very funny thing that did happen, the phrase, I think, was Gene Armour Pauley used it in an op-ed or an essay at one point, surfing the net. But there was a very interesting thing that happened to a company in San Diego, General Atomics. Back around 1989, they decided they would build a network for the Southern California area to connect universities together, and they were going to call it SURFnet. And they had a whole campaign with T-shirts showing people surfing and the waves going and everything else. And then about 3 weeks before they actually launched this system, they discovered that someone in the Netherlands had already taken the name SURFnet. It stood for Scientific Research Consortium, and they were supplying communications to universities in the Netherlands. So SURFnet wasn't going to work. So they said, well, why don't we just change our name to the California Educational Research Foundation Network? And it sounds the same when you say it. And then somebody says, well, why don't we call Vint and make sure he doesn't mind? So they called me. And my first reaction was, gee, if they screw it up, am I going to be embarrassed? This is a bad idea. Then I thought, wait a minute. people name their kids after other people, and if the kids don't come out right, they don't blame the people they named them after. So I said, sure, go ahead. And I flew out, and Susan Estrada, who was the executive director at the time, and I took one of these fake Hollywood bottles of champagne full of glitter, you know, the plastic stuff, and we smashed it over a Cisco router to launch the network.
One more question.
Since we're webcasting this and the archive will be available as soon as it's over on Ustream.tv under American Art, I want to get this answer into the permanent record. For people who can't stand the government spending money on anything, do you have any sense as to what was spent on the early development, and any sense at all of what the economic impact has been of that expenditure, what fraction, and where we'd be if that money hadn't been spent by the government, where would we be now?
You know, gosh, I don't know if we have any really
So
solid data.
The first increment of funding for the ARPANET was $1 million. Quite a bit more was spent over a period of time, but I don't know what the totals would be. $100 million maybe?
A couple of points. First of all, ARPA begins, right? And they don't really, DARPA does not spend a huge amount on the basic ARPANET and Internet development. The ARPANET, when it becomes operational, is literally paid for by the users of the net. Often ARPA, but often other agencies are footing the bill for access to the ARPANET. So it's not all coming out of ARPA's budget for operational purposes. In the case of the Internet, there was a very tiny contract initially at Stanford just to do the thinking through and documenting things and then trying to get protocols written more carefully. I don't think that that ARPA put much more than, say, an absolute maximum of $50 million into the original ARPANET work, at most, Now, the National Science Foundation comes along and wants to connect 3,000 universities around the country, and they're willing to pay for a network, to lease service from a network. Now that cost a bit more. They built that system. They had backbone networks constructed. That cost them probably another $50 million over a period of 5 years or so. I don't think that the research side of this added up to much more than a couple $100 million.
And the value is probably easily in the trillions, so there's a 10,000 to 1 payoff.
Well, thank you very much for coming and for sharing with us.